Okay, let's pick up where we left off. We're still in chapter 9. And last time we stopped, we were talking about a theory. And we're going to prove this one, just so we get some practice in about proving things about functions. So last time we left off there, we spoke about what bijective functions are. Then we moved on to inverse functions. So really we're still talking about inverse functions here. So we want to talk about some properties that they have. So this is sort of one way that we can know that two functions are inverses of each other. When you take their composition in either direction, you end up with an identity function. And so we're actually going to prove this, knowing that when this happens, we know that these two functions are bijective, and in fact, one is the inverse of the other one. So how do we prove it? Let's start with proving their bijections. Let's start with proving A, F is a bijection. And we can do this without loss of generality, since showing G is a bijection will be similar. So how do I know if F is a bijection? What do I have to show something's a bijection? Okay, so let's start. We need to show that F is one-to-one and onto. How do we know F is one-to-one?
Suppose it's not one-to-one, then you can find two elements of F that map to the same element in G, and therefore trying to map from G to, or sorry, two elements of A that map to B, and therefore trying to reverse that would not be a function since you have two elements, or one element that tries to map to two separate functions. Stop. That's not what we're trying to.
Okay, but then we'd have to talk about it in terms of things not being equal, which is sort of weird. You probably want to do a contradiction there. It's possible to do it by proof here. Talk in terms of equality. So that would work. I probably would write it in terms of a contrapositor or a contradiction to make it look nice, but
Formally, I was thinking of a contradiction.
Assume f of A equals f of B. I want to prove that A must be equal to B. How do we get that? Right, yeah, that's the same thing. F of A equals F of B. How do I get that A equals B? Use the composition. So if F of A equals F of B, what can I say then?
G of F
of A must be equal to G of F of B. But what do I know about G of F of A? It's A, right? G of F is the identity on A, which means if I plug in an element from A, I should get the element A back, right? But G of F of A is equal to A, and G of F of B equals B, since G of F is the identity on A, right? So if I plug an element from A into G, it just gives me the element back. But that just means that A would be G of F of A, which we know is equal to G of F of B, which is B. So ultimately we have that A equals B, so F is 1 to 1. How do we know F is 1 to?
Suppose that it's not.
You like contradiction, don't you? You're just full of contradictions. Okay. Let's try to do directly.
Well, since
What do we need to show? Assume that we have some B in B, right? F goes from A to B. I need to show for any element I pick here, there's an element over here that gives me that element. How do you think we get that? Let's look at G of B and assume G of B is equal to A. Right? How do I know that G of B even exists?
G of F of A.
Right, G is a function from B to A. Therefore, for every element in B, it is a part of the domain of G. Therefore, G of B does exist and it maps to A, so its output is definitely in the set A. Right, so G of B is definitely going to be in the set A. Okay. So now what? So use our assumptions again. What can we say?
Well,
Right, then if I look at F of G of B, right, what is that? That's just B. Because F of G is the identity on B. If I plug in an element in B, it just gives me the element back. So this means that F of G of B equals F of A equals B. So we found an element in A such that F of A equals B, which means F is onto. This means F is a bijection and G is a bijection and be shown. Right, so a very similar argument, except you use these, right, here we used G of F first, then F of G. If you flip it around, you're going to use F of G first, then G of F. It's going to be pretty much the same argument. So I can do it without loss of generality. So I know F is a bijection, G is a bijection. What?
you can also use that, like we showed before about if they're the same, like they're bijections if and only if they're the same size. And that means that they are the same size.
Right, but I don't want to restrict myself to thinking of finite sets. Right? So that theorem that you mentioned, remember, it only works for finite sets. So, but this would cover all cases, as you can see, the infinite sets. It's very arbitrary, and everything should fit together. So we've proven the first part, right? They are bijections. How do I know that G is actually the inverse of F though? now we show G equals F inverse, i.e., let's say if AB is in F, we need that BA is in G, right? And of course, vice versa would work in a very similar way, right? So let's actually prove that. Suppose AB is in F, right? This just means that F of A equals B. All right, so what can I do now? Okay. Then what?
G of F.
Then G of F of A
Equals A.
must equal to A.
You can then replace the F there with B into
This means G of B equals A, which means that BA is in G. This means G equals F inverse. So this is actually a very important property. It shows us that when we compose two functions and we get the identity, then we automatically know that both the functions are bijections, and in fact they are inverses of each other. Right? Showing that F is G inverse is pretty much the same argument, except you go backwards. It's not going to be much different. So it's a very important. They're not terribly too difficult to prove, so I thought I'd just show you the argument. Any questions on that? Okay, so let's do another example. Was this example? Let's say F goes from R minus 3 mapping to R minus 5. Defined by F of X is equal to 5X over X minus 3. A, find F inverse. B, conclude that F is bijective. Do A. How do you find F inverse?
Find some function for, like said, F of X minus X over X minus 3 equals to Y and solve for Y.
Yeah, basically you switch the outputs and inputs. So our picture here, let's say that's the set A and that's the set B. Then here, if I take this element as X, it maps to, under F, it will be F of X, but then under F inverse, this guy would be actually F inverse. You can sort of think of the inverse as living there. Here, it's sort of weird for me to just tell you to find inverse. So assuming it exists, right? Because technically, you can't just assume it exists. Okay, so let's actually do that. Find the inverse, and again, it's pretty much the same thing you've done back in calculus. It's not anything crazy. Alright, so assume y equals 5x over x minus 3, where y is an element of R minus 5. This means we can solve for x, so I just multiply both sides by x minus 3. And then I just want to isolate the x's, so I'll leave x over here, move this guy over there, move that guy over there. This means that x times y minus 5 equals 3y. This means that x equals 3y over y minus 5. Now, note. X is actually the f inverse of y, so that we can assume the inverse function of x looks like so we found the inverse function. Alright, switch output and input, solve for the new output. That's basically it. How can we conclude that f is bijective?
Isn't it like the definition that the function has an inverse function if and only if it's bijective?
Did I give you that theorem?
No, yes. That is only true with
We can actually use the previous theorem. The theorem I just proved can help us here. Right? You can actually check. I won't do the algebra, but you can check that if you take f of f inverse of x, as defined here, you'd actually get x and you'd actually get x and f inverse of f of x is equal to x. This means, by the previous theorem, f is a bijection. Is there something else? That's it. I want to make a note here. Yeah, it was yesterday. Yesterday, we did the example. It was very similar to this one.
just like x minus 2.
Yeah, it was just, so f went from r minus 2 to r minus 3, where f of x equals 3x over x minus 2. And we showed that was bijective. Right, basically I want to emphasize here that we can actually approach this problem of figuring out bijections in two different ways. We can either do it directly, show it's one-to-one or onto, or we can just show that we can find an inverse function. I just want to basically say that the moral of the story is to show that it is a bijection. You can do this in a couple ways. And basically you do whichever one is easier. In general, finding F inverse is difficult, but it might not be. So if that's the case where it's difficult, you might just want to go just by the original definition and prove something is one-to-one and onto. Otherwise, if you realize that you can actually solve for the input really easily, then just finding its inverse is the same as showing it's a bijection. So, just wanted you to have a couple of ideas. I even gave an example. Well, I'm sure you know examples where it's difficult. Example, f of x equals right? So that guy you have to basically, if you want to prove that that's a bijection, you have to sort of go show it's one-to-one and onto, which is sort of going to, it's going to be difficult as well, but finding F inverse is pretty much, you can't do the second way. Right? You have to use some other arguments. You probably use a few from calculus to help you out. But as you probably know, there's no general formula to solve a polynomial that's a fifth degree or higher. So finding that inverse, unless it factors nicely, which this one doesn't, it's impossible, basically. So just want to mention that. And now I want to talk about permutations. So that's all we have for inverse functions. I'm going to talk about permutations. And that will end our discussion of functions. Anyone knows what a permutation is?
Like a rearranging?
Yeah, it's a rearranging of terms. So the idea is we can think of this, we can think of a permutation. So I can arrange A in a certain order, but then I take a function that maps each element to some other element within the same set, and that defines a new order. So I can sort of think of this as a rearrangement. In fact, that's a definition. It's pretty much copying the same thing when I'm writing a permutation. so that is defining what a permutation is. It's just a bijective function, right? So, and we can think of it as rearranging the terms. We'll see why we can. So for example, let A be the set, A, B, C. Then look at the function alpha, right, which is typical for them to use alpha as AA, B, C, C, or anything with beta. Are permutations. And notice that here in alpha didn't actually rearrange anything. It just, everything maintained the same position. A was first, it's still, the second element is still there. B is first, then B, then C, then C. In B though, we actually rearrange the terms. So instead of A, B, C, we now have B, C, A, right? So you can sort of think of it as rearranging these terms. And it's just a bijection going from A to itself. The notation that we will use, there are other notations, such as cyclic notation, but we're not going to talk about that. So it's A, then alpha, A, B, then alpha, B, C, then alpha, C. So we can use that as the notation. So for example, I can look at alpha as this guy. ABC goes to ABC. And I can look at beta. This guy. ABC. Put them in a certain order. And then I go B, C. So I can actually write down those functions, right? So this just says A maps to A, B maps to B, C maps to C. Here A maps to B, B maps to C, C maps to A. Right? So I went from the arrangement ABC to the arrangement BCA. Right? And that is A bijection. Like I said, there are other notations to this, like there's a cyclic notation, which is very useful for certain things, but we won't care about that.
Cyclic notation?
Cyclic.
Oh.
Where you sort of break it down into cycles. When you do abstract algebra, you'll see that. Because you can tell a lot of properties about a set by how many cycles it breaks up into. If it's an even number of cycles or an odd number of cycles, it means certain things, but we won't care. That's not for us. So, more examples. What are all the permutations of the set of elements 1, 2?
1, 2.
Right, 1 can go to 1, 2 can go to 2.
Or 1, 2, 2,
1 can go to 2, 2 can go to 1. Right? That's it, they're just two of them, basically. What about if I looked at all permutations? 1, 2, 3. What's the first one? We just list them, 1, 2, 3 in order, then we go to itself, 1, 2, 3.
1, 2, 2.
Right, so I leave the 1 and then switch these two. 2. Another one.
2, 1, 2.
So put the 2 in the front and then 1, 3, and then of course I can switch the last 2. 2 in the front, but then to the 3 and the 1. Now I can put the 3 in the front.
3, 1, 2.
1 and 2. 1. That gives us all arrangements. There are 2 when 1 is the first element, there are 2 when 2 is the first element, there are 2 when 3 is the first element. So a set of 2 elements will have 2 permutations. A set with 3 elements will have 6 permutations. How many do you think a set with 4 elements will have? It's factorials, exactly. So this guy, a set with 2 elements will have 2 factorial permutations. A set with 3 elements will have 3 factorial permutations, and so on and so forth. This is sort of piggybacking on that theorem that we had where the number of bijective functions from a set to itself is n factorial. So let's just write that down. Note if A equals n, then the number of permutations on A is n factorial, because they're just sets of bijections. The set of permutations of 1, 2, 3, n is called Sn. Not called, denoted. It's actually called a permutation group, and again, if you do abstract algebra, you'll hear about this. Or the symmetric group, denoted Sn. So, for 1, 2, 3, Sn is literally just the set of alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, and the last example. So I throw all these functions into a set. The set of those functions is called S3. So S3 would look like that, right? So S3 is just a set of these 6 functions, right? S2 will be the set of these 2 functions, and so on and so forth. So I want to tell you about permutations. Note, you can compose So these guys are functions, they are bijections, which means they have inverses, we can compose them and things like that. So basically what we can do is with this notation, it's sort of easy to figure out what their inverses are and their compositions. We'll talk about that soon. So inverses, all you do is you swap inputs and outputs, right? So from here, the first step is you swap. Alpha 1 is up here, 1 is down here. Alpha 2 is up here, 2 is down here, alpha 3 is up here, 3 is down here, all the way up to alpha n is up here, n is up here. Then rearrange so that the first row is in ascending order. Okay, so how do you think we find alpha inverse?
Put the bar on top of that.
Yeah. So put 2, 1, 4, 3 on top, then 1, 2, 3, 4 on the bottom. And now basically you rearrange, right, by columns, so that the first row is in ascending order. Rearrange columns. So here's the column with the 1, I'm going to put that in the beginning. The column with the 2, I put that second. The column with the 3, I put that third. The column with the 4, I put that last. So that's actually the inverse function. That's basically how we can find the inverse when it's a permutation. Swap the inputs and outputs, rearrange so that it starts out with 1, 2, 3, 4.
Is the inverse function ever be different than the regular one? So that looks, since it's essentially the same function.
It can look different, yes. Let's look at composition. An example for that. Erase those. So let's do an example. I have X to compose a 3, which is 1, 2, 3, with 2, 1, 3. Six composed with 1, 2, 3. 2. So here's how we do it. We're just going to start from the guy on the right. Remember, it's following the same notation of f of g. It means you plug the g into the f. So we start here on the guy on the right. And we're going to start with the input here, and we're going to follow it through to the second one. So basically, we're going to see that 1 would go to 3, right? And then I take 3 as the input over here, and then I see that 3 goes to 1. 3 goes to itself, right? So 1 goes to 3, and then 3 goes to itself. So basically, ultimately, if I start at a 1, I end up at a 3. Right? So this would be 3. And you do the same thing here. 2 goes to 2. And then you follow where does 2 go? 2 actually goes down to 1. So ultimately, if I started at 2, I end up at a 1. So this is a 1. Same idea, 3 goes to 1. 1 actually goes to 2. So if I start with a 3, I end up going to the 2. So that is 2. That's basically it. So you start with the guy on the right, follow him to here, then follow whoever is there to here, and then put that as your answer. Right? So if I actually compose these two functions, this is the result. This is the composition of the two functions. So if I take the function 2, 1, 3, compose with 3, 2, 1, I end up with the function 3, 1, 2. And I should mention to compose two alpha i's. They have to be from the same SN, right? So I couldn't have this guy as a permutation on 4 elements and compose it with on 3 elements, because then where does the 4 go? There's no 4s on this side. So they of course have to be from the same symmetric group. So this is just to introduce the idea of permutations. We're not going to do a lot with it. In fact, I don't really want to do anything else with it. It's just going to be something that you're going to see in higher math classes. So I thought they introduce it here, but you're really going to do a lot of work with these guys in a class like abstract algebra. They form very, very important examples, and they're actually very, very useful for a lot of applications. And that finally ends chapter 9. So we're done with chapter 9 now, finally. So that was just another look at functions. Are there any questions from anything that was confusing? Not clear about functions? Okay, so the homework for chapter 9 is due next class, so we can look at those guys and see if there's anything tricky for you. We're going to move on to chapter 10. A very cool chapter. We're going to talk about the cardinalities of sets. Cardinalities of sets. we're not going to go too crazy here, because this is a topic that has literally put mathematicians in insane asylums. So we're going to realize some crazy things about infinity here, and it actually drove a lot of people crazy the first time they discovered it. So, but we're going to keep it very controlled, a lot of things that are widely accepted today, so it shouldn't be so bad. Try not to freak out and take it too seriously. Okay, all right. So, counting finite sets is okay, right? You have a finite number of things you can count. Then you might have to count for a while, but that's all right. But what if we actually talk about counting infinite sets? Then that's sort of a problem. And you might say, well, if it's infinity, what are we counting? Just say it's infinity and it's done. It's actually not that simple. As we're going to discover, there are different sizes of infinities. You can have different sizes. One infinity can be bigger than another one, right? Which is sort of interesting and crazy. But that's basically what we're going to sort of figure out. And how we deal with that is we actually use functions, bijective functions, in fact, which is why chapter 9 is very important. So the idea is, how do you actually count something that's infinite? Well, what we do is, we don't really count it per se, but we sort of try to figure out how big is it in relation to something else that we sort of know what size it is, right? So, and how we do that is we try to pair the elements off. So you can think of, in like a movie theater or something, right? So if I have a bunch of chairs, I have 10 chairs over there, and there are a bunch of people over here. I don't know how many people are standing over there, right? But I know I have 10 chairs, right? So what I do is I just assign each person a chair, right? You sit in the first chair, you sit in the second chair, you sit in the third chair, and so on and so forth. Now what's going to happen is, what I'm actually doing is I'm creating a function, right? The set of people is the domain, the set of chairs is the codomain, right? And I'm actually assigning it in a one-to-one fashion, right? Now there are a couple of scenarios that can happen here. One, I can run out of people before I run out of chairs, right? In which case, I really didn't know how many people there were, but I know there were less people than there are chairs, right? So the number of people had to be less than 10, right? Or I can run out of chairs before I run out of people, in which case I don't know how many people there are, but I know it's more than 10. It has to be more because I exhausted all the chairs over here before I exhausted all the people. There's also the case where now I assign each person a chair, and I run out of people and chairs at exactly the same time. So what does that mean? I know for sure now there are 10 people, right? So it's a way of counting without actually counting, right? I can just count the number of people in relation to the number of chairs, right? So that's sort of the idea, how we can know if something has more elements than another thing, or less elements than another thing, or exactly the same elements as another thing, right? So that's sort of the idea. If you sort of carry them off with a function, and if it turns out that your function is a bijection, it's one-to-one and it's onto, everyone there gets exhausted by choosing everyone here, then I know they're exactly the same number of elements. If it's the case where I try to put these guys in a one-to-one relationship and I end up with, I run out of elements here before I run out of elements there, it means the elements over there were more than the elements over here, right? And that idea is what we use to talk about the infinite case, right? The fact that we can sort of pair off elements in this way. And that's sort of where we're going to start. So, talk about a definition. That's sort of going back to that example I just gave. Two sets, A and B, are called said to have the same cardinality. In this case, we write the size of A is equal to the size of B. Right? So this is talking about two sets, and I can compare them in terms of size. I can know they have the same cardinality, that is the same number of elements, and we can say they're numerically equivalent if I can find a bijective function from one set to the other. They're either both empty, in which case their size is both 0, right? Or if they're non-empty, then if I can find a function that goes from one set to the other that's bijective, meaning it's in a one-to-one relationship, and all the elements here exhaust all the elements there, it turns out they will have the same number of elements. Right? So that's the idea. One thing that you should be aware of we call it numerical equivalence because it's actually an equivalence relation if we set things up this way, right? So if I set things up so that a set A is related to a set B, if there's a bijection from A to B, it's actually an equivalence relation, right? And it's not actually hard to show this. How do you show that this this is reflexive, this relationship? Well, that's for symmetry. What about reflexive? How do I know that A relates to A?
Oh, the identity function.
The identity function, right? A relates to A. Since if I take F from A to A with F where F is just the identity function on A, then F is a bijection. Right? Just send every element in A to itself. It's a bijective function. What about symmetry? Right, so suppose F from A to B is a bijection. Then so this is saying A relates to B, right? There's a bijection from A to B. How do I show there's a bijection from B to A?
Well, there's an F inverse or a G equals F inverse.
Right. F inverse exists and is also bijective. We have a theorem that tells us that. This means F inverse from B to A is a bijection. So it's symmetric. What about transitive? So if we assume there's a function from A to B, that's a bijection, and a function G from B to C is a bijection, how can I get from A to C? Composition. Then which one? G of F is a function that goes from A to C is a bijection. Right? And then we proved this as well. I think yesterday we proved that. Where we showed that if F is 1-to-1 and G is 1-to-1, then the composition is 1-to-1. And if F is onto and G is onto, then the composition is onto. Therefore, the composition is a bijection if each function in it is a bijection. So it's actually an equivalence relation. It's actually equate to sets this way. So they are actually equivalent in terms of cardinality. So another thing do I want to mention that yet? Another thing we're going to talk about are denumerable sets. The set A is called some other definitions first. Probably didn't introduce this earlier, but a set A is called finite if A is either the empty set or the size of A is n for some n in n. So that's a finite set, and A is called infinite if it is not finite. Now let's talk about the numerable sets. Okay. So what does this mean? The size of A is the size of n. Yeah, what does that mean? What does that mean is possible?
It means that you can put a one-to-one relation.
Right, there's a one-to-one correspondence from A to n. There's a bijection that goes from A to n, or from n to A. There's a video either case. So, note A must be infinite. Also note usually going from n to a is an easier way to set up a function, but you can go the other way as well. And now to define a new terminology that I heard someone mention, the set A is called countable. If it is either finite or denumerable. So every finite set is countable. Also, every denumerable set we'll call as countable. Countable basically means listable. We can list the elements of a set, right? Now, whether it's finite or infinite, we can do this if it's going according to n, because we can literally just number the elements and call them out in a list. So, example. Suppose A is finite, then from n to a by, I can think of f as being, well, 1 gives me some output in a. 1 goes to f of 1, 2 would go to f of 2, 3 would go to f of 3, etc. So this will basically mean that a, I can think of the elements of a in terms of the outputs of this function. It's f of 1, f of 2, f of 3, going on forever. And I just rename these guys, right? Call this guy A1, call that guy A2, call that guy A3, and it goes on forever, right? So if A is denumerable, it's actually listable, right? I can just list the elements. This is the first one, that's the second one, that's the third one, that's the fourth one, that's the fifth one. And I can write them off in a list, right? So if a set is denumerable, you can basically assume it can be written this way. You can order the terms and you can number them all. You can list them all, right? So even if it's infinite, the idea is you can still arrange everyone in order and list them off. Sure, you might be listing forever, but it's possible to do it. A set that is not countable is called uncountable. Right? Now these are the crazy guys, the uncountables. These are the guys that are so infinite, you can't even write down everyone in a list. You can't write them down in a list. Every list you can possibly make for these guys, you'll always be missing someone. You'll always be missing an infinite number of people in any given list that you can write down. You cannot list them, right? You can't do this for these guys, right? So that's crazy. So they're actually a lot bigger than these guys, like by a lot, right? So even n, you can list the elements of n. It turns out that for the real numbers, you can't list the elements of the real numbers. They're actually much bigger than n. And we're going to get there eventually, but I just want to introduce that. Just in case you might see this. Sometimes people, in other texts, you might see them just call things countably infinite. It's the same thing as denumerable. Not a lot of books use the word denumerable, but they might say it's countably infinite, right? It basically means denumerable. So in case you're reading other sources, that might come in handy. Okay. So let's actually look at some denumerable sets. As it turns out, the integers are denumerable. So, it can take a while for this to sink in. Basically, I'm saying if we only look at all the positive integers, then it actually has the same number of them as if we throw in all the negative integers and 0 as well. Right? They're the same number of elements, exactly the same. They're the same size, right? So all integers has the same number of elements as just the positive integers. How do we prove this? Show there's a bijection, right? So basically you can actually prove, you can find a function that goes from the natural numbers to the set of all integers that is 1 to 1 and on to. And here, sometimes identifying these functions in a formula can be difficult, so sometimes we describe them in diagrams or schematics or something like that, and they actually work here. So consider the function f defined by, you can actually put a description of f to say how the function is assigning elements, right? Once you can assign it in a predictable way, it's good enough, right? So if I list all the elements of n here, right? And I just say what each number maps to, right? So 1, I'm going to send to the integer 0. 2, I'm going to send to the integer 1. 3, I'm going to send to the integer -1. 4, I'm going to send to the integer 2. 5 to the integer -2. 6 to the integer 3, and so on and so forth. Right? So it turns out I can actually list the integers in this way, right? Start at 1, then go +1, -1, +2, -2, +3, -3. I can actually write them out in a list. Notice that each element in the integers will appear in this list eventually, clearly. And it's actually a one-to-one function, right? There's only one number that will go to 0, right? Because all the elements are increasing after that, right? So it's actually one-to-one. And it's actually onto. Every element here will appear eventually. Then f is one-to-one and onto. It means I can list the integers. They actually form a countable set. Alternatively, note that from n to z defined by So I'll leave it up to you to verify, but that's actually a function in terms of a formula that goes from one set to the other set. So there are a couple ways you can do this. Once you can actually describe exactly how your function will assign elements, and you can give an argument for that it's one-to-one and onto, sometimes it's really obvious. You can say, oh, they're clearly the same thing, right? They're clearly have the same size. I can list the elements of Z, right? This is my A1, A2, A3, A4, A5, A6, going on forever. And every element will appear, and every element will appear in the second row exactly once. It's a one-to-one and onto function. So, in conclusion, the size of n is actually the same as the size of the integers. Finding a formula is often very tricky, right? So they might actually find it sometimes, but otherwise, describing it in a very predictable way is good enough. Because the functions to come up with a nice closed form formula can often be very challenging. Any questions on this? So once I can show that there's a set and I can write the elements in a listable form, and they happen to be infinite, then it's the same size as n. Well, there's another theorem. I'm not going to prove that theorem, but maybe I can sort of illustrate it with another example. And then we move on. So if I go in the integers and I only pick out the even ones, it turns out that that's the same size of all the integers. It's also the same size as n. How would I prove that?
Well, the definition we've been using of even integers is a bijective set between the natural numbers.
So how would you assign these guys? So 1 I can send to like 0. Right? Then this would go to 2, minus 2, 4, minus 4, 6, so on and so forth. Right? So I can also list the even integers. Right? So notice that the size of n is actually the same as the size of z, which is the same as the size of v, which is the same as the size of O. These are the odd integers. In fact, the size of k times n every such set is a denumerable set. Right? So if I look at all the multiples of 2's, they're denumerable. All the multiples of 3's, they're denumerable. All the multiples of 4 or 5 or 6 or 7, they're all denumerable sets. They all have the same size. So you can actually select just the multiples of some integer that you want, and you actually have the same size of all the integers. That's sort of the weird thing about infinite sets. You can have proper infinite subsets. This is true in general in some sense. Which I won't prove this, I'll just tell you the theorem. Every infinite subset of a denumerable set is also denumerable. i.e., if A equals n, and B is a subset of A, B is infinite, then it turns out that B will equal n. The size won't change. Right? You can select a subset, once it's infinite, it will still be the size of n. Right? So you can throw away an infinite number of guys and you still have the same amount of guys. So the proof is in the text. It's not that bad, but it's too long. I don't really want to waste time writing it down. So you can read it, and if you have any questions, you can ask me. But they basically defined a function that selects the elements of P, is essentially what they do. And then they show that that function is one-to-one and onto, and they can connect it to n, they can list the elements. So that's actually a very important thing And in fact, these two facts are corollaries of this idea, right? Because these are just, this forms an infinite subset of n, that forms an infinite subset of z, and therefore they're infinite subsets of denumerable sets, they're also denumerable. This theorem gives us this pretty easily, and this theorem we can prove. Let's see, what else do you want to talk about? Here's another theorem, an interesting one. If A and B are denumerable, then A cross B is denumerable. The Cartesian product of two denumerable sets is also a denumerable set. You'll have a denumerable set of ordered pairs when you pair together two denumerable sets. So the proof is here, all we have to do is describe a function. It'll probably be hard to do it in terms of a formula, but once we can show that there's a predictable and concrete way to actually identify the elements and list them together, then that will be good enough for the proof. The idea is, since A, B are denumerable, we can list the elements. So I can write A as A1, A2, A3, and I can write B as B1, B2, B3, forever. So now what I do is I try to list them. B1, B2, B3, B4. B1, B2, 3, 4. So I create a grid, and I'm going to create all the ordered pairs here. So A1, B1, A2, B1, A3, B1, A4, B1. It continues like that forever. And so now the idea is, how do you define a function that actually counts the elements here? Well, you can do it in the following way. Count along the diagonal here. That will actually define a function, right? So for example, I can say define f so that f of 1 is going to be the first guy we hit, so that's going to be A1, B1. F of 2 is going to be A1, B2. F of 3 is going to be the next guy that we hit. A2, B1. F of 4 is going to be the next guy that we hit. A1, B3. F of 5 is going to be the next guy, A2, B2, and so on and so forth. Right? And I can literally just rename these guys. So this guy I call, and just A again. So this guy I can call C1, call this guy C2, call this guy C3, call this guy C4. This guy's C5. Then that means A cross B, I can actually write as these elements C1, C2, C3, C4. I can list them, going on forever. This means the size of A cross B is actually the same as the size of integers. I can actually map 1 to C1, 2 to C2, 3 to C3, 4 to C4, and that will be a bijective function. So if I have two sets who their sizes are the same as the natural numbers, then their Cartesian product will be the same size as the natural numbers. The size of their Cartesian product. And believe it or not, we can extend this. We can take the Cartesian of 3 sets. It's still the numeral. Cartesian product of 4 sets, still the numeral. Right? You can take any finite size Cartesian product we want. It'll still just be the numeral. Right? Which is, seems crazy, but it's not. Maybe I have time to show you this. Right? By next class, we're going to show you that the real numbers are bigger than the integers, things like that. Talk about uncountable sets. The positive rationals are denumerable. That is the set of all positive fractions. There's the same number of them as the set of natural numbers. So the idea here, very similar to over there. We know that the fractions are formed as from the ratios of integers. So I can line up the integers in the grid. And so what I can do is take the numbers along here as the numerators, the numbers along here as the denominators. So this gives me 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1. This is 1 over 2, 1 over 3, this is 1 over 4, 1 over 5, 2 over 2, 2 over 3, 2 over 4, 2 over 5, 2, 3 over 3, 3 over 4. And the idea is, again, here we just define a function that will start to count these guys off for us. There's one hiccup though, but it's easily dealt with. The idea is some of the numbers will repeat. Just define your function in such a way it skips over a number if it's actually a repeat. So the function is going to actually skip this guy and just move on to the next, right? Because 2 over 2 is the same as 1 over 1, right? So once it chooses 1 over 1, your function is going to skip everyone else along this diagonal because they're always going to be the same. And is there another one that it will skip here?
4.
Right, it will skip 2 over 4 because we already got 1 over 2, right? And so on and so forth. So
4 halves.
it would also skip 4 halves. Who else would it skip? That's it in this picture, right?
Yeah.
So here, our function will literally just count these elements. So you can sort of list the elements now. So this guy you can call, C1. That's your C2, your C3, your C4, your C5, your C6, your C7, your C8, your C9. Right? And you can literally count them off, right? So here, this means your Q plus is just this set, C1, C2. You can list off the elements. Let's not use C, since we already use C. Let's use Q. this, we can get another theorem. It turns out the size of Q is the same as the size of N. The size of all fractions is the same as the size of all positive integers. And then since by above, we know Q plus, we can list the elements Q1, Q2, Q3. Define f by this function. One I'm going to send to 0, which is also a rational number. 2 I send to Q1, 3 I send to minus Q1. 4 I send to Q2, 5 I send to minus Q2, 6 I send to Q3, 7 I send to minus Q3, and it will continue in this way. So ultimately, in about, I don't know, 10 minutes or so, we've shown that n is the same as the size of z. It's actually the same as the size of q. It's actually the same as the size of the positive rationals, the positive integers, right? You can do that as well. It's the same as the size of k, z, or the same as the size of k, n, k not equal to 0, k, etc. Right? So these are all infinite sets, and they all have the same size. They all have the same number of elements, and we know this because we can find bijective functions from one to the other. And once I can find bijective functions between any two, they're equivalent. So any pair, we have an equivalence relation here. So by doing a function from this to this, or this to that, this to that, I can get from this guy to anyone else in this list by taking a composition of functions. Right? It's just like that. Yeah. So that's where our journey starts, and it'll get crazier next time. So we haven't finished chapter 10, obviously, but chapter 9 is done, so homework for that is due on Monday. And we'll finish chapter 10 on Monday as well, hopefully.